Okay, let's talk about the central limit theorem. Okay, it all goes back to sampling error. And just to review, because sample statistics do not exactly equal a population parameter, then we have sampling error. Again, it doesn't mean you've done anything wrong. It's always going to be there. It's just a function of taking a sample from a population. We don't expect the sample statistics to equal population parameters. Also, with any population, we could sample potentially infinitely from that population, and the amount of error that we would observe is going to vary from sample to sample, and as a result, that forms a distribution of sampling error. So that's what we call the sampling distribution of the mean. Okay, it's a theoretical distribution of sampling error when estimating the value of the population mean from sample data. Not just the population mean, but also the population standard deviation and variance. So how much error should we expect? Well, the central limit theorem tells us this. Okay, and it's probably the most fundamental principle in all of statistics. And basically it says, okay, sampling error is a function of two components. The first is the population variance, and hence its standard deviation. And then the second is the sample size. So it's really these two components that contribute to overall sampling error. Now, one of the nice things about the sampling distribution is that it's normal, and that's true even when the underlying raw score distribution for a variable is not normally distributed. And we'll talk about that in the next video. But really the takeaway just for now is that sampling error is a function of the amount of score variation and population variance in the population, and then the sample size that's taken for the actual sample. So here's a formal statement of the central limit theorem. For any population with mean mu and standard deviation sigma, the distribution of sample means for sample size n will have a mean of mu and a standard deviation of sigma divided by the square root of n, and will approach a normal distribution as n approaches infinity. Now there's a lot there, but let's walk through it, okay? So we have a population, right? And for any population, population mean is called mu. Of course, that distribution will have a standard deviation. That's sigma, okay? All of this should be really familiar because this is what you've covered so far in descriptive statistics, okay? Now, if you start taking means from that population distribution, then you're going to have a distribution of sample means, right? And your sample is going to have a particular size, that's n, right? So the distribution of sample means is specific only for a specific sample size. If you increase your sample size, then that distribution might change a little bit, okay? Now that distribution of sample means, again, this is the sampling distribution. It's theoretical, right? You never actually collected all these sample means. It's theoretical. We're going to estimate this using some math, okay? For a sample size n is going to have a mean of mu. In other words, the mean of the sampling distribution, right, is equal to the population mean, mu, and a standard deviation of sigma divided by square root of n. Okay, now we're going to call that standard error of the mean. Okay, so this is not actually called a standard deviation. It's called a standard error. Okay, so, but it can be interpreted the same way. Okay, but just be aware, we're not talking about standard deviations at that point because that's relevant to raw score distributions. Now we're talking about standard errors. Okay, now the distribution is going to approach a normal distribution. In other words, it's going to become more normal as n gets bigger. Okay, and that should be fairly obvious from the formula. You know, as n gets bigger, this denominator right here is going to get larger as well. Okay, and that's going to shrink the size of the standard error and the distribution becomes more normal. Let's just take a look at what this all means with regard to the estimate or the standard error based on a distribution in which there's a standard deviation of 10. Okay, now down here on the horizontal axis, okay, we have the number of scores in our samples, so that's n. Okay, and you'll notice that as n goes up, okay, the standard distance between a sample mean and the population mean, in other words, the standard error, goes down. Okay, what that means is as n increases, the expected deviation or difference or error of the sample mean from the population mean becomes less and less. And once you get up to about 36 or so, it starts just beginning to plateau, right? You're always still going to have error. That's why this line here never touches the horizontal axis. But it's going down, it's decreasing, and then it kind of plateaus out and gets smaller and smaller and smaller. You know, and really that happens right around n equals 30 to 40, somewhere around there. But the takeaway from this graph here is just to say, you know, as your n increases, your standard error decreases, which is a good thing because we want our sample means to be as close in estimation to the population mean as possible. Okay, so we can say right now, big N's, large N's are good things. We like large N's in statistics. Okay, so what are the implications? The greater the population variance and the population standard deviation, the greater we should expect the sampling error to be, right? So the more variable the population is, the greater the sampling error is going to be, and sampling error will be smaller, of course, when observations in the population take on more similar values, are more consistent, and there's less variation. So the standard error of the mean is going to tell us how much sampling error we should expect given the sample size and the population variability. And if we change either of those, we're going to get a different distribution. And you can interpret the standard error of the mean as the standard deviation of the sampling distribution of means. Okay, implications. What can a researcher control? I mean, we know we're going to have sampling error, and we want to minimize it as much as possible. You know, the problem is we have really no variability over scores in the population. I mean, the population is what the population is. It's either going to be highly variable, less variable, not a whole lot. Our job is really just to measure things. So we can't really control the variability of scores in the population. What we can control is sample size. So the sample size that we collect, which we know is related due to the central limit theorem to sampling error, we need to increase our sample size as much as possible. So larger samples are better because they minimize sampling error. And larger sample sizes are especially needed when the population shows large amounts of variability. Okay, big picture. Central limit theorem tells us that sampling error is a function of both sample size and population variability. The more variability in the population, the greater the sampling error is going to be. And by that, we just mean that on average, we expect a greater distance between sample means and population mean. The larger the sample size, the smaller the sampling error. And the standard error of the mean tells us how much sampling error to expect given the sample size and the population variability. Standard error of the mean is the standard deviation of the sampling distribution and can be interpreted as such. So you can interpret the standard error of the mean pretty much the way you interpreted the standard deviation in a raw score distribution, but they're not the same thing, right? Because what we're plotting out is how much sampling means are expected to deviate from the population mean. That's different than saying a raw score from a population mean. Okay, next thing we're going to do is talk a little bit about the shape of the sampling distribution. I'll see you there.